Okay, what we're doing here is called the meter sensitivity lab, but really the whole purpose of this is to learn how to take a galvanometer and turn it into a voltmeter and an ammeter. A galvanometer is just a really, really sensitive voltmeter. It only takes a few millivolts to make the needle deflect. In order to use the galvanometer as a voltmeter, we need to connect it to a resistor. In order to turn it into an ammeter, we need to connect it to a resistor a different way. So before we can even start, we need to measure three things about this galvanometer. Those three things are VG. VG is the voltage that it takes to get a full-scale deflection. You can get a full-scale deflection to the right or to the left, depending on the polarity. So VG is a special voltage for this galvanometer that makes it deflect all the way to the right, full-scale deflection. It takes a certain number of volts to do that. Another thing that we need to measure is IG, which is the current that flows through this thing when it's full-scale deflection. So when you get a full-scale deflection of the galvanometer, it takes a certain amount of current to do that for this particular instrument, and we need to measure that. The other thing we need to measure is RG, which is the internal resistance of this galvanometer. So let's measure those three things first, and then we'll talk about how to turn this into a voltmeter and how to turn it into an ammeter. Okay, so the first thing we want to do is to measure the voltage that it takes to make this go full scale. What we have here is a resistance box set at 10,000 ohms. You can see the little 1 here, 1 times 10K. We're going to just make a simple series circuit from the galvanometer through the resistance box, through the battery, and then back to the galvanometer. What I'm doing here is in your lab manual is starting on page 32. And you can see here's the little circuit. It's very simple, just a simple loop, a single series circuit with a power supply, which is just a D-cell battery, the galvanometer, and the resistance box. So we're going to connect these things all in series. Here's the battery. Make this a little bit longer to the galvanometer, and you can see the galvanometer is deflecting. So we want to make this deflect full scale so we can calculate the voltage it takes to do that. So to make it full scale, we need to reduce the resistance of the resistance box. So what I'm going to do here is just fiddle around with the knobs, and you can see the galvanometer is changing when I do that. And you can see it's getting bigger now because I'm decreasing the resistance. I got to be careful not to get it too far. We're almost there. I'm going to look at it head on here. Need just a little bit more resistance to bring the needle to the full scale. That full scale means all the way over to the 50 mark. That's very close. Okay, so now we have full scale deflection. So what do we know? We know the voltage of the battery, and we know the resistance. We can just read the resistance off here. We've got 2 thousands, 8 hundreds, and 6 tens. It's 2,860 ohms. That's for the resistance box. And so, Ohm's law says V equals IR, right? So what we can get is the current, I equals V over R, where V is the battery voltage and R is the resistance in the circuit. So one of the first things we need to do is just measure the battery voltage. So we're going to take these leads, turn the voltmeter to the voltage side. 2 volt setting ought to do it. It's just one battery. I'm going to turn it on and just measure that battery voltage directly. Okay, it's 1.48 volts, and that's a number that you should write in ink on page 33 of your lab manual. So battery voltage, just write 1.48 here. And I'm going to do that because we're actually going to do some calculations here. 1.48 volts. Okay. And the resistance that we just measured, what resistance is this? It's the resistance that makes the galvanometer go full scale. And we saw that that was 2860 ohms. So I'm going to write that, and you should write this in your lab data sheet in ink. 2860 ohms. Oops, I wrote 6860. I'll just cross that out. 2860 ohms. Now we know, or we can calculate, the current that flowed through this loop to make it go full scale. So the current through that loop, the calculation is just E, which is the voltage of the battery, which you can find on your data page, 1.48 volts, divided by the resistance that we saw, 2860 ohms. Now I need to do the calculation. Okay, so now we're able to calculate IG, 1.48 volts, divided by 2860 ohms, which gives us a very small number, 0.517 milliohms. So IG, 0.517 milliamps, I should say. It's a current. It's really, really small, which means the galvanometer is very, very sensitive. So it has a current of that value. So now we know one of the three things of the galvanometer that we need to know, what's called a full-scale current. Okay, so to find the resistance of the galvanometer, we just follow the next procedure, which is to connect another resistance box in parallel. And you can see from your handout, that's what we're doing right here. This is the original circuit we were just using. Now we're going to connect another resistance box in parallel with the galvanometer. So in parallel means we just connect the leads right straight across, here to here, and here to here. And we're just going to follow the instructions as they're written. Connect another series of resistance in parallel with making S equal to 300 ohms. So we're going to set this galvanometer to 300 ohms. Here's the hundreds switch. We'll set that at 3. Set everything else to 0. So we've got 300 ohms. And connect R1 and set as before, and adjust S so the galvanometer reads exactly half scale. Okay, so what we're going to do is we're going to set it up just like before with a series circuit going to the battery and through the galvanometer. Actually, let me put this parallel one last. So we're going from the battery into the galvanometer. There we have our full scale deflection like before. Now, when I connect the second resistance box into the galvanometer, let's see what happens. Look at that. The galvanometer is reading less because some of the current's going through the resistance box. Not all of it is going through the rest of the circuit. So here's how this works. If I decrease the resistance, more and more current flows through the parallel resistor box and less through the galvanometer. Now, the instructions say I should set it to get a half-scale deflection. So I'm adjusting the parallel resistance box to make the galvanometer read 25. Okay, I'm going to reduce this a little bit. Okay, so now it's reading half scale. So what does that tell me? It says half the current's going through the galvanometer as before, and the other half's going through this resistor. Well, in fact, exactly half of the current is going through this resistor, and other half is going through this resistor. What does it tell us about the resistance of the galvanometer and the parallel resistor? Right, it tells us they're equal. Okay. So the reading on this resistance box must equal the reading of the resistance of the galvanometer, because the current is split exactly 50-50 between the two. So I'm just going to read off the numbers here. Let's see, we've got 0 thousands, we've got 0 hundreds, we've got 4 tens, and 8 ones. That's 48. So it's 48 ohms is the resistance of the galvanometer. So I've got two of the parameters we need to know for the galvanometer. We've got the full scale current and the resistance. So given I and R, how can I find full scale voltage of the galvanometer? Just through Ohm's law, V equals IR equals 0.517 milliamps times 48 ohms. And that's going to give me 24.8 millivolts. So this is our VG, 24.8. That's how much voltage it takes to make the galvanometer go full scale. Okay, so the main goal of what we're trying to do here today is to convert this galvanometer into a voltmeter and then convert it into an ammeter and to see if they actually work. Just a quick review of how to set up a voltmeter and an ammeter. If we've got a typical circuit here with some kind of voltage, we've got some kind of resistance here. This is our voltmeter. Now we're going to use the galvanometer, which is really sensitive, but if we just stuck the galvanometer directly into this circuit, the voltage is so great here, it's way bigger than the full scale deflection of the galvanometer, so it would just blow the galvanometer. So to protect the galvanometer and make sure it doesn't exceed the full scale value, this is our galvanometer. What we're going to do is put a series resistance here, which we're going to call RS. We're going to put a series resistance in series with this galvanometer. Now we can safely connect it across the resistor and measure the voltage drop across it. So the goal here is to choose what value of resistor would turn this into a voltmeter. And it kind of depends on how many volts we're expecting to measure. So suppose we want to measure a maximum of 5 volts. So I'm going to call this R desired. That's our desired resistance we want to measure, maximum of 5 volts. So how would we do that? Well, it turns out there's a handy little formula that you can find on your page 35 of your lab manual. And it says the series resistance we're looking for is just Vmax. Okay, this isn't a resistance, this is a voltage. We want to measure a voltage with this. The maximum voltage is 5 volts, desired max. So the resistance that we need to read that voltage maximum is just the desired maximum voltage divided by the current of the galvanometer. Okay, so this is what we're looking for. The resistor that'll change the galvanometer into a voltmeter. This is how many volts we want to measure, and this is the galvanometer current, the maximum scale full deflection galvanometer current. So we know these numbers. This is 5 volts that we want to be able to measure. And the galvanometer current maximum deflection is 0.517 milliamps. So that's going to give us a resistance. Now this has to be a big resistor. All voltmeters have a very large resistance to keep the current from flowing through and burning out the galvanometer. So we're expecting a large resistance here. And in fact, we get 5 divided by 0.0005117 amps, and that gives us 9.67 k ohms. So if we connect 9.67 kilo ohms in series with our galvanometer, it will become a voltmeter that can measure 5 volts. So let's do it. I'm going to take this resistance box. I'm going to set it to 9.6 k-ohms. So here's the 10K setting. So if I go to 9, so I've got 9,000. $670. Turn the others to 0. Now we have 9,670 ohms. We calculated what resistance needs to be in series with the galvanometer to make it into a voltmeter that reads 5 volts. So now we're going to test it and see if it actually works. What we have here is the battery. This is our voltmeter. The galvanometer connected to the resistance box in series. We take the 2 leads, and it's now a voltmeter. So I'm going to touch it to the battery. We know it's about 1.48 volts. And I touch it to the battery. You do it the other way so it looks good. Notice the deflection on the galvanometer. Since the maximum reading is 50, but we want a 5 volt meter, we're going to call 50 5 volts. And you can see where the needle is. It's between 1 and 2 volts. Actually, it's reading about 1.6. The true value is 1.48, so that's experimental error. But the point is, we now have a voltmeter that can read up to 5 volts. On the battery, it's reading about 1.6 volts. So you should write that down on your data page where it says the reading of the galvanometer. And then the percent difference will be between the reading on the galvanometer and the true voltage of the battery, which we measured before. Okay, so we just made a voltmeter from a galvanometer by calculating the resistance needed in series to make it work. So now how do we make an ammeter out of it? That's a little more complicated. In order to make an ammeter, remember, the ammeter needs to be in the circuit of whatever circuit we're dealing with. Let me draw it a little bit better here. Here's our battery. Here's our ammeter, our resistor. So the current needs to flow through the ammeter in order for the ammeter to register the current. But if we take the galvanometer and just put the galvanometer in the circuit, what do you think is going to happen? Well, obviously, all that current flowing through the galvanometer has a maximum current that it takes of 0.517 milliamps. If we put 3 amps through that, it's just going to burn it up. So what we need to do is take the galvanometer and put another resistor, not in series like the voltmeter, but in parallel with the galvanometer, a really, really low resistance, which we can call S for shunt. So we take a really, really low resistance. Most of the current is going to flow through that and bypass the galvanometer. So the galvanometer only reads a small voltage across this shunt resistor. So there's a formula for calculating the value of that shunt resistor that'll change our voltmeter, our galvanometer, into an ammeter. And that formula is given on page 36 of your lab handout. Now it looks like this. The shunt resistance is going to equal to the galvanometer voltage. That's the maximum fluctuation of the galvanometer, the voltage we calculated before, divided by the maximum current desired to measure. Now, how much current are we going to want to measure here? It's calling for something that measures about 0.5 amp. So I max desired. So the voltage of the galvanometer is the full-scale deflection voltage that we measured from before is 0.108 volts. And what we want to do is we want to make an ammeter that'll measure up to 0.5 amp, 0.5 amps. So the shunt resistor that's needed to do that is just 0.108 divided by 0.5, and that's 0.216 ohms. So theoretically, if we take our galvanometer and connect in parallel to it a resistance of 0.216 ohms, it'll become an ammeter that can measure half an amp. The problem is you can't buy a resistor that low. You can't just run down to your local electronics store and order a 0.216 ohm resistor. We have to make our own resistor. So to do that, what we have here is a piece of copper wire. Now, if we were doing this in the lab, I would have you calculate the length of the wire needed to create a 0.216 ohm. Why are we using copper wire? Because a copper wire has low resistance. And it turns out this length of copper wire is exactly what we need in order to create a 0.216 ohm resistance. So what I'm going to do is connect this copper wire as a parallel resistor for the galvanometer. And I'm going to do that just by connecting one side of the wire to this connection, like so, and the other side of the wire to the other side, like so. Now we have a resistor in parallel with the galvanometer. The resistance the wire has a really low resistance, so most of the current is going to flow through it, bypassing the galvanometer. And supposedly, this can now read a current of up to half an amp. Okay, so we have our homemade ammeter here, connected just like it shows in the picture on page 37 of your lab handout book, where you have the power supply going into the galvanometer, which is now an ammeter, from the ammeter through the real ammeter, or store-bought from a professional manufacturing company, from there through a rheostat, and the purpose of this thing is just to control the current to get the values that we want. Don't worry about that. And it comes right back into the power supply. So if you notice on your data page, it asks us to bring the current up to these values, 0.2, 3, 4, and 0.5, to see if our two meters agree. If they agree, then we have success. We've made an ammeter that measures what we want to measure. So what I'm going to do is bring the power supply up on the store-bought meter to 0.2 amps, which is the first one that we're supposed to get. And I'm going to read it off of our homemade meter. So remember, we wanted a maximum of 0.5, so 50 now represents 0.5 amps. So here's 0.1 and 0.2, and it looks like, wow, it looks like it's right on, 0.2. So on your data page, you should write 0.2 amps on our meter. So let's continue up to 0.3 on the homemade meter. And we're getting, it looks like maybe 0.305, close enough to 0.3, we can just call it that. Anyway, 0.4 gives us 0.4, and 0.5 on the store meter gives us 0.5. So it's working perfectly. That's the whole point. In your lab handout, your lab write-up, you should talk about these results, point out the fact that the homemade meter measured all those currents just the same as the ammeter, which means it's really working. So in the write-up, you want to talk about everything that we did, how we measured the three parameters of our galvanometer, how we converted it into a voltmeter, what the results were, how close they were, and then how we converted it into an ammeter. You might want to talk about why did we need to use a copper wire for this, and so forth. Okay, so that's pretty much it for Meter Sensitivity Lab.